Good afternoon, my name is Adrian Sims and I'm here today to talk to you about proportional balancing. As with all things LEV, our first port of call is to see what HSG 258 says on the matter. For balancing, it's pretty vague. It says it's highly skilled work, and Chapter 8 goes on to say that balancing must be done by the installer/commissioner, and that most common cause for systems to be out of balance is because someone has adjusted a damper. It also advises on further reading the American guidance. Looking at the American guidance provided in ACGIH manual, which is available from Amazon for about £120, gives two methods: balance by design and what they term the blast gate or orifice plate method. The balance by design method does not use dampers. It requires the designer to ensure each branch to a common junction has the same static pressure. To achieve this, they will modify the duct diameters or volume flow rates, i.e. the velocity or the components used in each branch. This generally results in lower static pressures, so therefore you can get away with a lower kilowatt rating on the fan and save energy and money. However, it is very difficult to get right on a multi-branch system and leaves no room for alterations from the design layout. It also often requires a higher total air volume flow rate than the damper option. Whilst not very popular, you may come across this method where the system is handling explosive or radioactive dust or biological material, as you do not want any obstructions which may cause accumulation of contaminant in the duct. The balance by blast gate / orifice plate method needs a bit of explanation. In the UK, an orifice plate is a flow measuring device. However, the ACGIH manual describes an orifice plate as a fixed blast gate. Each branch can be designed having differing static pressures, so adjustments to the system can be made between design and installation. An orifice plate is added to give a predetermined static pressure to balance out the branches. After each orifice, a blast gate damper is fitted. However, the orifice plate requires approximately 5 diameters of clear duct either side to ensure the flow through is predictable. Adjusting the blast gate will alter the air volume flow rates in all the other branches of the system. This method generally results in higher static pressures, resulting in higher kilowatt rating on the fan and using more energy and costs. As this method is used where only a fraction of the hoods are in use at any given time, it can lead to reduced velocity in the header ducts that can lead to blockages. To avoid this, you may see air bleeds on systems. This is to allow additional air into the headers when branches are shut off to ensure that there is no dropout in the header duct. Also available is the testing and balancing of HVCA of air and water systems. This is a copy of the 2014 or 5th edition and is available on Amazon for about £80. Being HVAC, this is aimed at the general or office ventilation systems. When they talk about capture hoods, they don't mean our type of capture hoods. They're talking about the cones you use to hold over ceiling grills to enable you to measure the airflow through the grill. It does lay out the principles of proportional balancing and talks through the process about ensuring all dampers are open, identifying the branch with the lowest percentage of design volume flow rate, adjusting dampers in the system to ensure that all branches are moving the same percentage of the design volume of air volume flow rate. Closer to home, the CIBSE TM42 fan application guide, which is free for iLevi members to download from the CIBSE Knowledge Portal, or £50 to non-members, covers a lot of good guidance that is very relevant to LEV design, such as fan type selection, fan curves, noise, fan laws, and taking airflow readings. In my opinion, should be part of any LEV engineer's library. Unfortunately, it does not cover very much in terms of balancing, but it does have a good description of system resistance, which is important to understand when balancing systems, as it is the resistance to the airflow through each branch that we are relating to when looking for the index circuit. It is the branch with the highest pressure loss that will have the largest percentage deficit when compared to its design duty that will be our index duct. This guide does give us a reference to CIBSE Commissioning Code C. Unfortunately, this is either a typo or has been updated, as Commissioning Code C is for automatic controls. The one you really need is Commissioning Code A. Again, as an iLeaving member, this document is free to download from the CIBSE Knowledge Portal, or it's £58 for non-members. It does refer to an older text by Harrison and Gibbard, and it goes on to describe the process of proportional balancing as it consists essentially of working back to the fan from the remote branches, setting the correct proportional airflow at each junction of the system in turn. The key element to remember here is that you are not looking to measure the actual flow rates at this point. Only once you have balanced all the branches proportionally do you look to adjust the fan total volume flow rate to obtain the required design volume flow rate. The code does give worked examples and provides a detailed step-by-step guide which summaries to check all dampers on all branches are fully open, run the fan at full speed, measure and record the fan total volume flow rate. It should be greater than the design figure. If not, then you may have problems later on. And to measure the velocity at each hood based on common density and temperature. Now, things such as wind on the stack, filter resistance and even fan motor voltage can all have an effect on the system performance. So it's important that the initial measurements and when you come to the final measurements are all carried out in one continuous operation so that they are comparable. The initial readings can be very valuable. They will give you an indication as to if there are any issues such as noise, excessive system resistance, either through blockages or poor design and installation changes, or any leaks in the system. The issues will need to be rectified before you can balance the system. These readings will also indicate the extent of the balancing that is required and identify your index duct. Before we go any further, we just want to talk about the index duct. The CIBSE code gives a definition of the index duct as the terminal or sub-branch or branch in a distribution system which, prior to regulation of the airflow, receives the lowest indicated percentage of design fluid flow rate. It is important to remember that it is the percentage of the design volume flow rate we are talking about, not the actual volume flow rate, nor the velocity, but the percentage of the design volume flow rate. Once you have the system ready to balance, you've taken your initial readings, you remove the blockages and all the dampers are open. We've identified the index duct. We then turn our attention to the branch with the greatest percentage of design flow and close that one down a certain amount. We next need to check the effect on the system by remeasuring the volume flow rates in each branch to find out what effect that has had on the system. What we will find is that closing the damper has increased the resistance through this branch and will result in more air being moved through the other branches. A word of caution: when adjusting dampers, we need to give the air time to find its natural path. This normally takes a few minutes for it to settle down. Once you've taken these readings, compare them with the index duct. Unless you're extremely lucky, you will probably need to adjust more than one damper and often more than once. Every time we adjust a damper, we need to retake all the readings to establish what is happening. We call this a pass. Eventually, you will get to a point where all the branches are within about 15% of the index duct. At this point, I would go and have a break. Leave the system for about half an hour, allow the air to settle, and when you come back, retake those readings again, and you'll find that they would have adjusted slightly. At this point, you're probably going to want to fine tune the system. Be careful, dampers in LEV systems are not very sophisticated. In HVAC systems, we use what is called opposed blade dampers. These are very efficient at balancing the airflow through them, and they minimise turbulence. However, we tend not to use these in LEV for a couple of reasons. One, dust and debris in the air will smash or block them. And two, they're normally manufactured from aluminium, so could corrode in certain environments. We tend to use the more basic single plate damper, sometimes called the butterfly damper or throttle valve. These dampers are not linear. What I mean is that if you close them down by 30%, you do not reduce the airflow by 30%. They're very basic. They are just a flat blade in the airstream. You have to play around with them and see how they behave. Some are better than others. You will find that there are full rounded blades, and there are others that tend to have the edges of the blade trimmed off. The reason for this is turbulence. A full rounded blade tends to give more turbulence than a blade with a straight edge. Often, the damper will have markings to show how far open or closed it is on the handle. There are a few other things out there which you may come across that may also leave you scratching your head. Plenums are used on fume extract systems, but only where there is no particulate passing through the system. Otherwise, due to the drop in velocity through the plenum, they will actually act as a dropout box. There are advantages of using a plenum. Branch ducts can be added, removed or relocated at any convenient point along the plenum. Modifications are only limited by the total air volume flow rate and the pressure available at the fan, compared to the tapered main alternative that will require ducting modifications to the header duct. It can also be used as a dropout box before passing through the filter or a fan. However, material dropping out in the box is not ideal unless it is specifically incorporated in the design. Lint, dust can build up and be a fire risk, whereas other materials such as metallic dust, grain or wood could prove to be an explosion risk. So best to keep these for fumes only. In the case shown, each of the 4 branches coming into the plenum will be balanced against each other, and so you need dampers on each branch connecting to the plenum. Something else you may see is an air bleed. Air bleeds should be used to reduce the temperature in the system or to provide additional airflow to help convey heavy material loads in the main header duct. Alternatively, they may be added to enable a future connection or left over from a branch that has been removed. Either way, you will need to treat them as any other branch, and they will need to be balanced accordingly. Not all systems require all branches to be in use at the same time. Quite often, to improve efficiency and to save costs, you will have a limited number of points required in use at any given time. The exact number should be agreed with the client and specified at the start of the design process. Now, this may lead to blockages in a taper system when a transport velocity is not maintained. This should be taken into account by the designer. When balancing these systems, carry out the balance with all branches open. Once balanced, shut down the branches not required. This will force the air to come through the open branches, increasing the velocity through those branches. So based on what we know, here's a worked example of a simple 3-point system. I have tried to show 3 different types of hood. Hood A is a receiving hood, Hood B is a partial enclosure, and Hood C is a capture hood. So each hood will require a different air volume flow rate to make it work. Our first step is to find the index duct. The design engineer should be able to tell us which one it is, as they would have used this one to calculate the size of the fan. If not, then we can check this or find this ourselves. To find the index duct, we need to open up all the dampers on every branch, and we measure the velocity at the face of each hood and calculate the air volume flow rate passing through that hood. So the first row of numbers are the design air volume flow rates we require at each hood. And on the far right hand side here, you will see there's a total air volume for the system. It doesn't matter when calculating the air volume whether you work in meters cubed per second or, as I have here, meters cubed per hour, so long as you're consistent with your calculations. Once you have the air volume flow rate at each hood, you can then compare that with the design figures for each hood. As you can see in this example, hood A is 40% of this design duty, hood B is 70% of its design duty, and hood C is 340% of its design duty. So we need to adjust the hood with the greatest air volume flow rate compared to its design, which in this case is going to be hood C. We will close the damper at C, which will increase the resistance through that branch, forcing more airflow through the other two branches. Once we've adjusted the damper, we need to allow the air to settle to find its natural path through the system. This will take a few seconds to a few minutes. We can then re-measure the velocities at the face of each hood and recalculate the air volume flow rates and the percentage of the design duty. We repeat the process until we are happy that all the hoods are doing the same percentage of the design volume flow rate. It doesn't have to be the correct volume flow. Hopefully it's higher than you need. If it's lower than you need, then you may have issues with the fan, especially as filters start to get dirty. Eventually, you will get to within 10 to 15% of all the percentages being the same. At this point, I'd recommend you go and have a tea break and leave the system for a while and just let things settle down. Keep adjusting the dampers does affect where the air is coming through the system, so just leave it, let it settle. Come back after half hour, retake your readings, and you'll find that you just need to then fine tune the system. This is where you need to be careful. If the dampers are almost closed, they could be at a tipping point when the slightest movement will throw them and you'll end up with no airflow through a certain branch. So it's always good to record the position of each damper before you adjust it, so you can always move it back to where you moved it from. Once you're done and you're happy with all your airflows and everything's balanced, you're probably within 5–10%, you then want to record those positions, record your final readings, record the damper settings, mark the dampers, lock them into place, and even photograph them to put them into your commission report. Balancing is a long process. Lots of things affect it and vary the airflows in the room, especially when you're dealing with low velocities. Simple things as people walking past, other air movement within the room, all affects it. So it can take a very long time to balance a system. A good balancing engineer will probably take 3 or 4 passes of a simple system to get it balanced. So once you're done, once you're satisfied that everything's in balance, lock it all in place, record it, and then you can put those figures, those photographs into your report. So if anything changes, you can go back to those original settings. A couple of top tips when doing balancing. First thing I would say is use a spreadsheet. You're going to be doing lots of maths, calculating areas, velocities. You're not just taking one reading in the center of the hood, you're taking multiple readings. You need to work out the average. You need to compare that with the design volume flow rate, so you're working out percentages. It's wide open for making mistakes. Create yourself a spreadsheet, put the numbers in the spreadsheet. You can set the spreadsheet so it gives you the percentage of design flow rate, and you can see what dampers you need to adjust next. The next tip is to have a colleague with you. If you're going to be filling out these spreadsheets or doing all this maths, you want someone who you can use to be going up and down ladders or up and down in a cherry picker, reaching these test points, reaching the dampers, taking all the readings, while someone else records them down. So you probably want 2 people to do this job. And also, if you're in amongst production lines, you've got to move scaffold towers or move ladders or move cherry pickers around. So it's not really a one-person job, it's probably a two-person job. You're also going to want to try and do it when it's quiet. If the plant is running or you've got people around, that it will affect the airflows. It becomes very, very difficult. So normally out of hours or when the plant is in a shutdown condition. Next, to be patient. It takes time. You can't really rush these things. Small, simple systems, yes, you can probably do them within sort of 2 or 3 passes, or a good balancing engineer will. More often than not, you're going to be doing sort of 4, 5, 6, 7, 8 passes, especially on complex systems. So be patient with it. Allow the air to settle. Take your readings. You will get some anomalies. You will get some oddball readings at first. That's what balancing is. And you just, work them out. See what's happening with the airflow. See what the damper settings are, and just be patient with it. And the final one, and I can't stress this enough, and that is to record the damper positions when you've finished. People will adjust them. They do get moved. People will add and take off branches. People will play around with it. Even if you lock the dampers in place, people will find a way of moving it. So mark the damper, lock them in place, take a photograph of it, record it. I can't stress that enough. So to summarise, proportional balancing requires you to find the index branch, which is the path with the highest pressure loss. You're then going to close all the other dampers down to get the same percentage of design flow as that in the index circuit or the index branch. Once you've balanced the system and they're all within an acceptable tolerance, you're then going to lock the dampers and record their position. Thank you for listening, and I hope you enjoy the rest of the conference.